Okay. As people trickle in, I'll introduce our first speaker today, who's Kung Yi, coming back to visit us. Kung Yi is right now a research assistant professor at CIERA, Northwestern University. He received his PhD from Caltech and later joined as a joint Flatiron and Columbia postdoc fellow. And afterwards, Kung Yi was a BHI fellow at Harvard, and he left just earlier this last year. So his work uses galaxy simulation to study black hole accretion and feedbacks, which focuses on bridging scale physics between black hole and galaxy scales, and on how associated cosmic ray physics shape AGN feedback and galaxy evolution. So this is exactly what he's going to talk today. Thank you.
Hello, everyone. I'm Kong Yisu. It's my great pleasure to be back. Thanks very much for having me. It's a great pleasure to be back after several months of living here. And so today I'll be talking about some of the bridging scale work that I've started while I was a BHI fellow here. It's largely collaboration with a bunch of people here, like Heron, Priya, Ramesh, and Cora, and Angelo, and a lot of people that you know, and also Phil. He was here like the past few days. So yeah, I'll be mostly talking about the galaxy side of the story, how through bridging scale from galaxy to event horizon scale, how do we, from that, facilitate a more physically oriented AGN feedback model through this bridging scale work, and what is the implication of the galaxy evolutions and also black hole growth from these kind of AGN feedback. So I think
maybe click the screen.
Pardon?
Click on the screen.
Click on the screen.
Yeah.
Okay.
Now we should.
Okay, thanks. So yeah, so I know, so to model the AGN feedback, we all know that it is a huge, it's a problem with a huge dynamical range. First, we need to model and capture the accretion and inflow from the large galaxy scale all the way to the event horizon, while also try to track the feedback and outflow back from event horizons back to the galaxy scale. And this could be easily over 8 orders of magnitude and even more for a specific system from the VO radius all the way to event horizons. Taking like M87 system, for example, the VO radius is roughly at a scale of megaparsec, whereas the event horizon scale is roughly of the scale of milliparsec. It's easily over 8 orders of magnitude and even more. If you think about them in the time evolution times, for things in the galaxy scale, things typically evolve at a scale of like gigayear, whereas in the event horizon, things could be evolved within days. So it's a huge dynamical range, and it's traditionally very difficult to have a coherent simulation framework that capture the scale and physics of the galaxy scale while resolve everything down to the event horizon scale. So what do people traditionally do? People traditionally separate into two kinds of simulations. One of them is the galaxy scale simulations. Simulation of these kind of scale, people typically heavily rely on the sub-resolution modeling of the black hole feedback, which means that based on the density, temperature, and other physical quantities that can be measured around a black hole in a scale that is resolvable for galaxy scale resolutions, we just assign a black hole accretion rate. This could be something like Bondi type model or gravitational type model. So based on these empirical scaling relations, we just assign the accretion rate based on the density, temperature, and so on and so forth that is measured around a black hole. And based on what is accreted at a black hole at a galaxy scale, we just prescribe some of the, we just return part of the accreted mass or energy into arbitrary form as a feedback, as an AGN feedback model. And for the model in this scale, we typically require a lot in tuning the parameters, basically tune the functional form of the accretion model, and also how much of the energy to return per unit of accreted mass, and tune these parameters to make the galaxy look right, to make the statistical quantities matching some global observables, at least statistically. But these kind of models, typically there could be a lot of uncertainties, and there could be degeneracies that multiple models could possibly work. We know that TNG, but they also have their favorite model. They all sort of works. And also the resulting model might not be actually what happened in the galaxies. On the other hand, there's another category of simulations. These are when you zoom into the black hole vicinity and you resolve the event horizon, resolve the celestial radius. There's another category of simulations. These are general relativistic magnetic hydrodynamic simulations. With these kind of simulations, you can, for the first principle, launch AGN feedback pouring by black hole spin and magnetic field. So you do not need to put in the AGN feedback by hand. These feedback could be launched from the first principle of physics. But again, traditionally, the drawback of these kind of simulation is that due to computational cost, it can only be converged to a very finite volume. And also, this simulation can only be run for a very limited amount of times. So traditionally, there's a huge gap between the galaxy simulations and also the event horizon scale simulations. You either have the cosmological context, but you do not have a first principle oriented feedback model of AGN, or you have a first principle oriented AGN feedback, naturally launched, self-consistent launch from the simulations, but you do not have the cosmological context. Historically, there's not much communication in between until the recent development. You might have heard Heron's talk through the novel multi-zone method that Heron showed. She's here, and you might have heard a lot from her talk. But I'll briefly talk about the method. With this novel method, for the first time, we can actually track both inflow and outflow all the way from the event horizon scale to the galaxy scale. So the method to the zeroth order goes something like this. The fundamental problem is that you want to integrate the super small time step around a black hole vicinity to the cosmological timescale at gigayear. So we say that, so she said instead of evolving the whole simulation box all at once, you separate the simulation from galaxy scale to event horizon scale into different analyte. And one of a time, only keep one of the analyte alive and freeze things within that specific analyte. And by iterating up and down the scale several hundreds of times, eventually she get a converged solutions all the way from the event horizon scale all the way to the galaxy scale. So in a sense, this is sacrificing the full time evolutions of the whole system, but more or less get a quasi-steady state solutions from galaxy to event horizons. And this is already very informative for the galaxy side. This could facilitate now a physically oriented feedback model now propagate from the event horizon scale to the galaxy scale. Yeah, so you can see this one of the example of the simulations. And after getting this method, we apply it to more realistic galaxy environment. This is an M87 galaxy simulations capturing the scale and physics from the megaparsec scale all the way to the 100 parsec scale. We run a simulation a little bit and use it as an initial and outer boundary conditions for Heron's novel multi-zone GRMHD simulations, which then take over from kiloparsec scale all the way to the event horizons. And after these multi-zone iterations of several hundreds of times, we capture the resulting inflow and outflow as a subgrid model, which we can put back into the galaxy simulations. Let's choose specific quantities that we use. One of them is how much of the mass actually reached the black hole vicinity. So the Bondi accretion rate is something of the inflow rate at a Bondi radius. But from this multi-zone method, we find that only less than 1% of the mass actually reached the black hole vicinity. So that is a very huge dramatic suppression of the accretion rate from the Bondi radius scale all the way to the event horizon scale. Another quantities we measured is how much per unit accreted mass will be returned into feedback at a Bondi radius. For spin zero case, back then for this first loop, we only have the spin zero case. Now we have much more. I will talk about them later. But for the spin zero case, we measure feedback efficiency of 0.02. Again, a pretty low feedback efficiency, but just for the spin zero case. And after that, we put these quantities, how much of the mass reached black hole, and how much of the energy is returned to feedback back into the identical galaxy simulations of M87 kind of setup. You do see the feedback propagate to large radius. And if you further quantify them, the resulting simulation, this is the black hole mass as a function of times, black hole accretion rate as a function of time, net increase of the black hole mass as a function of times, and the net increased stellar mass as a function of times. So you can see there's a lot of lines here. I'll go one by one. First, as a reference, if we just put in a Bondi accretion without feedback, surprisingly, the black hole quickly overgrow, following the red line here. You start with something reasonable for M87 setup, but it quickly overgrow to some unphysical value. On the other hand, if you just suppress the black hole accretion without putting any feedback, you just suppress the black hole accretion to be 0.01 Bondi without putting any black hole feedback, you just marginally postpone the overgrowth of black hole, since that the gas inflow from large scale still build up the density around the black hole, and eventually, although you suppress the accretion rate, those gas will eventually still be swallowed by the black hole. So you just marginally delay the overgrowth of black hole. On the other hand, if you have some feedback, even from the spin zero case of a 0.02 feedback efficiency, that is already sufficient to sustain a very steady state of the black hole mass over gigayear time scale. You can see that a black hole roughly stay at a gigayear at its initial mass of 4 gigayear time scale. But if you want to further match the Event Horizon Telescope suggested value of the black hole accretion rate highlighted by this gray region, you need slightly higher feedback efficiency. You measure something roughly 0.15 to 1 that is sufficient to sustain a black hole accretion rate roughly matching the Event Horizon Telescope result. And also, unsurprisingly, also the higher the feedback efficiency is, the more dramatic the suppression of the star formation rate is. Okay, so what do we learn so far? We learned that from this first loop from the galaxy side to the event horizon scale with this multi-zone method and put that back in the galaxy scale, we learned a few things. One is that if there's a supermassive black hole that is already at its redshift 0 mass and is already embedded in a full-grown cluster ellipticals, it can sustain the steady black hole mass over gigayear time scale, even with a very low feedback efficiency of 0.02. This is roughly the spin 0 case. And with slightly higher feedback efficiency, roughly 0.15, definitely would need black hole spin for that. It can also crunch star formation and also have a black hole accretion rate roughly match the Event Horizon Telescope result. So these are all great, but there's still a few missing pieces. One is that would a black hole grow into this redshift 0 supermassive black hole from the first place while quenching the star formation in the process of the coevolution of galaxy and black hole? And also, we haven't talked much about the spin dependence of the efficiency. And also, so far, we only keep a uniform suppression of the black hole accretion, which is 1%, but we didn't take account for the variability of the environment around the black hole, right? So there could be possibly some environmental dependence of the suppression of the accretion rate, which we not yet considered yet in how we talk about so far. So again, Haren have solved a lot of these problems. She later ran a huge grid of simulations with the multi-zone method and surveying different environment around the black hole and also different black hole spin. So now with these huge grid of runs, we now have the full scaling relations of how much of the mass is actually suppressed when we reach the black hole, depending on the local quantities. So the scaling relations goes like the Bondi radius over Schwarzschild radius of minus a half scaling. So this basically means that the larger the separation of Bondi radius with respect to Schwarzschild radius, the more dramatic the suppression will be with respect to Bondi accretion rate. And also from different black hole spin, she also gave us a grid of data of how much of each case the feedback efficiency should be. Spin 0 case, this gives a 0.02 feedback efficiency. For the maximum spinning black hole, this arrive at a feedback efficiency of roughly 0.3. So with this, this already give us a full grid of parameters of the AGN feedback that we can use readily into galaxy scale simulations. So to test these problems, we then, to test these in a cosmological context, we test them in a zoom-in simulations of the redshift 0 halo mass of roughly 10 to the 14 solar mass. We have a huge grid of runs, which we survey different feedback efficiency. Now from the minimum spinning black hole with the efficiency of 0.02 to maximum spinning black hole with a feedback efficiency of 0.3. And also we now put in the full environmental dependence of the suppression of Bondi accretion rate for those that actually reach the black hole. And we also try different seeding mechanisms to try under which circumstances will the black hole grow while also quench the galaxies reasonably. So the fiducial case is like one of the thousands of the stellar mass. We see the black hole mass, we see the black hole. So when the stellar mass reaches roughly a few 10 to the 10 solar mass, we see the black hole of roughly 1,000th of that. We also compare a few different scenarios. One of them, we have a lighter seed of black hole. When the stellar mass reach, again, roughly the similar mass, we see a stellar mass of a few 10 to the 6 solar mass. This is one of a 10 to the 4 of the stellar mass. And we also have another case that we see the black hole earlier and more massive. So when the stellar mass reach a few 10 to the 9 solar mass, we now see one of the hundredths of the stellar mass as a black hole mass, which is a few 10 to the 7 solar mass. So with these huge grid of runs, again, you can see very interesting result from first the movies. So this is the fiducial seeding case. Left-hand side, this is the low feedback efficiency case. Again, catering to the spin 0 case. Right-hand side is a higher feedback efficiency case. Again, roughly comparable to the maximum spinning black hole case. You can see upper panel, this is the temperature profile. Lower panel, this is a number density profile. You do see that over the right-hand side, with higher feedback efficiency, the black hole feedback and AGN feedback is much more energetic and propagate to larger radius. And if you further quantify them in the statistical quantities, like in the black hole mass over stellar mass plane, this is one of the thousands. This is the local stellar mass, black hole mass, stellar mass relations, and also the stellar mass over halo mass function. The gray region is empirical function. If we further plot these runs in these diagnostic plane, you see that again as a reference, without any feedback, just by the accretion itself, the black hole will quickly overgrow, unsurprisingly. But again, and also without any feedback, you wouldn't quench the star formation, right? The stellar mass at higher halo mass n will be overproduced, as you can see from the magenta line here. Again, as a reference point, no feedback, you definitely overgrow the black hole and overgrow the stars. And now, if you have a low spin, minimum spinning black hole, then what happens is that the black hole will roughly follow the local stellar mass halo mass relation, following these green lines. But the problem is that since the feedback efficiency is very, very low, the black hole doesn't quench the star formation. You still see a very overpredicted stellar mass at these higher halo mass end. On the other hand, if you have a maximum spinning black hole, the feedback efficiency is much higher. So then now the galaxy kind of quench at a higher halo mass end. But the problem is that the black hole doesn't accrete much. As you can see from its initial black hole mass, the black hole doesn't grow much via accretion at later times. These later vertical lines are emergent event. These are not accretion event. So with these, assuming this is the only feedback and accretion channel, what you encounter is a dilemma that either in a low spinning black hole case, the black hole grow but not quench, or for high spinning case, the black hole quench but does not grow. So you fall into these dilemma, assuming this is the only feedback channel. And a lot of these problems is fall into these huge suppression of the black hole accretion rate. So again, as a reminder, the black hole accretion rate from this novel multi-zone method, we predict the scaling relations of R bar D versus Schwarzschild radius to the 10 to the minus a half. And if you put it into temperature, you can rewrite this in the temperature form. This means that at roughly 10 to the 7 Kelvin, the suppression factor is roughly 0.01. And the lower the temperature is, the more dramatic the suppression of the accreting mass to the black hole will be. Which means that at most 1% of the mass actually reach black hole. And when the temperature goes lower, it'll be more dramatic suppressions. And if you actually measure what is the actual suppression factor, you measure in the simulations according to the local temperature, you see that it is suppressed by over 2 orders of magnitude and easily over 3 orders of magnitude when in the simulations. So due to that very little mass actually reach the black hole, it makes the black hole really hard to grow while quenching simultaneously. And it is so dramatic a suppression that if you start a black hole with lighter mass, like instead of starting in the a few times to the 7 solar mass, if you start with a few times to the 6 solar mass, even if you turn off the feedback all at once, the black hole also wouldn't grow by much, right? So if you start with a 10 to the 6 solar mass, even without any feedback, the black hole barely grow throughout the evolution of the systems. So it make that if this is only channel or feedback, it make the black hole really hard to grow, especially before it reach supermassive black hole a few times to the 7 solar mass. So what is the way out? Observationally, we definitely see supermassive black hole. We also see quench full-grown galaxies. So there's definitely some way out of this dilemma. There's a few way out. One of them is that these feedback channel might not be the only channel of feedback that of the black hole. So these GRMHD-informed feedback model is mostly applicable to sub-Eddington accretion rate kind of environment by design of the GRMHD simulations. So there might not be applicable, these scaling might not be applicable to transient super Eddington case. And we possibly need a separate treatment of a cold or super Eddington accretion. And this is definitely necessary before the black hole reach a few times 6 solar mass. Otherwise, the black hole wouldn't grow at all. And also another way out is possibly you can track black hole spin. So we say that for low spinning black hole case, the black hole can grow. For high spinning case, the black hole can quench. And maybe by tracking the black hole spin, you can have some episode that black hole will grow and some episode that the black hole will put in a lot of energy and quench star formations. And the third way out is possibly that we can just have an earlier and more massive seeding of black hole, so the black hole can start more massive at early universe. So for the third scenario, we've tested a little bit and it sort of worked. So as a reminder, originally the dilemma goes like this. The black hole either grow but not quench or quench but not grow. But if you start a black hole at early universe, although the black hole still doesn't grow much by accretion, but this vertical line, this merger event itself might already be sufficient to reconcile with the local stellar mass halo mass relations. And meanwhile, since you start the black hole at earlier times and more massive at earlier times, you also better quench the star formation, better match the empirical relation of the stellar mass over halo mass function. So this is one of the possible way out. But again, to reconcile the full picture, you might still need a separate prescription of the cold or superacting accretion, especially before the black hole reaches supermassive black hole. So again, as a quick summary, what we learned so far was this novel multi-zone informed AGN feedback model, which gave us a physically motivated feedback model we can be putting into galaxy serial simulations. We find a few things. One is that if the black hole is already at its redshift zero mass, it is super reasonable. It can reproduce a steady state of black hole mass over giga-year time scale, even with non-spinning black hole. It can match the Event Horizon Telescope result with some very reasonable spin and reasonable feedback efficiency. But if we include the cosmological context, you very easily encounter the dilemma that a black hole either quench but not grow, or grow but not quench. And this is especially the case before the black hole reach a few times the 6 solar mass black hole. And possibly have earlier heavy seeding possibly help this picture. And tracking black hole spin also possibly helps. But we definitely need a separate prescription of the super Eddington or cold accretion before the black hole reach supermassive black hole from the first place. So yeah, I think I'll stop here and take any questions. Thanks.
Sorry, our microphone doesn't work, so you'll have to shout if you have a question. Anyone in the room has a question? Yeah.
Are you planning on actually tracking the speed, or is something that is not planned yet?
Yeah. So Heron now.
Repeat the question for Zoom.
Okay. So it was asked that what is the spin coming into the picture here. So I think Heron now have a huge grid of runs with different black hole spin. So different spin zero case is 0.02, maximum spinning case is 0.3, and definitely now for the galaxy side of the runs that I've run, I fix a spin, which means I fix a efficiency.
Yeah.
But down the line, we definitely want to have like a live tracking of black hole spin as the galaxy evolves. And yeah, that's very much in planning. But yeah.
Actually, I have a quick question. Did you, from your lower mass seed merger scenario, how many mergers do you need to account for the system?
Yeah, I haven't counted that, but I can quickly. Yeah, I think maybe a few, maybe starting from a few times away. Yeah, maybe like one each vertical lines maybe is one merger-ish. So I think several mergers.
And this is over a similar time scale.
Yeah, I run all these simulations to roughly redshift 1. So it's from like redshift 6, 7 to redshift 1-ish. Yeah.
Thank you.
Yeah.
And any other questions?
Yeah, sorry. So can you remind us in terms of the geometry of the accretion flow, like the physical intuition behind the fact that, you know, you cannot actually get so much material to be feeding the black hole. So in terms of this temperature argument that you made, this is me coming also from like an X-ray reflection background, so not necessarily expert on M87 and Sagittarius.
Yeah. So I think from the geometry result that you sort of get these kind of scaling relations, which means that the like how this number quantify how much of the suppression of black hole accretion rate from the Bondi radius to the spatial radius. At Bondi radius, you get an inflow rate roughly comparable to the Bondi accretion rate. But in the spatial radius, that inflow mass is largely suppressed. A lot of them get returned in the form of feedback. So very minimum inflow only get to the Bondi rate to the spatial radius. And I think Heron get these kind of scaling relations. The larger the Bondi radius is compared with the spatial radius, then it means that there's a huge larger suppression. So, and she get a density profile. So it means that it means that the larger this suppression is, the more dramatic the suppression with respect to Bondi accretion rate it will be. And the hotter the temperature is, the less the suppression with Bondi radius and spatial radius will be. So that will be a minimum suppression with respect to Bondi. But the larger this separation is, it means a more dramatic suppression. So like if the temperature goes 10 to the 5 or 10 to the 6, then it means that the accretion rate largely suppressed with respect to that.
Okay,
Yeah.
thank you. And you have throughout the talk, you have highlighted a lot of results in relation to M87, but are you
Yes.
planning to
Yes.
expand this to like future BEX targets?
Yeah. I think so far I've run most of the isolated galaxy simulations in M87 kind of setup and Milky Way like setup, but definitely we're planning to run a whole array of ones, and we're very much ongoing in testing them. Yeah.
Okay, yeah, let's thank Kong-Yi again. And
Thanks so much.
that's something that
Thanks. If you need my pointer also.
I should be good with thanks.
Oh,
Sorry.
so while Anthony is setting up, I'm very happy to introduce him. So Anthony Flores recently finished his PhD at Stanford University and is now a postdoctoral researcher at Rutgers University. His research focuses on using current and next generation SE surveys to identify samples of galaxy clusters at high redshift for targeted multi-wavelength follow-up. His primary expertise is in using X-ray observations of the intercluster medium to explore cosmic evolution out to the highest redshifts available with existing cluster catalogs, and using these studies to plan for the next generation of missions. Anthony is from the East Coast originally, but hasn't been visiting the CfA for a while. So we're very happy to have him here. So thanks a lot for coming.
Yeah, thank you. This is actually my first visit to the CfA, which is very fun for me. Yes. But no, it's great to be here to chat with you all. I'm also here for through the rest of the day if anyone has any questions or wants to meet and chat about things. But for today, I'm really excited to be here to be able to tell you about my X-ray work with high redshift clusters. And so to give some context for why we want to obtain X-ray observations of these systems, here's a few examples. These are ground-based optical images of clusters spanning redshifts about 0.4 to 1. I grabbed them all from the sample, the spectroscopic BCG sample compiled by Michael Calzadilla here at the CfA. So these objects also have complementary Chandra exposures, and when I overlay those X-ray data, you're better able to see the underlying structure of a galaxy cluster through the intracluster medium, or ICM. The ICM is very hot, easily reaching tens of millions of degrees. It's a diffuse optically thin plasma that, because of its temperature, radiates at X-ray wavelengths, and it is the dominant component of the cluster's baryonic content, so much more so than the galaxies themselves. And that means it can tell you quite a bit about the internal structure and properties of galaxy clusters. So over the course of this talk, I will focus on what we can extract from these X-ray data to tell us more about the evolution of clusters over cosmic time. To start, these X-ray observations of the ICM are useful to us because the hot intercluster medium is the most direct probe of the thermodynamic state of massive galaxy clusters and groups. And that is extremely important to our understanding of feedback processes in the universe. As clusters evolve, they strongly affect the environments in which their member galaxies reside, and then in turn can be affected by the energetic output of their own members through supernovae or active galactic nuclei. And this means that X-ray observations of the ICM provide a unique probe of the effects of feedback on clusters over their lifetimes. For example, we can examine the instantaneous effects of feedback on galaxy cluster environments, for instance, through the cavities we can see in the intracluster gas that are produced by expanding bubbles from AGN jets. But we can also recognize that there can be many generations of these bubbles, and the energetic output of galactic processes can actually reach incredibly large scales. So as the cluster is growing gravitationally via mergers and through accretion, these feedback effects can also have a very strong impact on the current state of the cluster when you essentially integrate all of those processes up to the moment of observation. And so the most complete tests of cluster evolution, especially in the context of these feedback processes, requires you to make measurements as a function of redshift in order to directly compare between the local and the high redshift universe. One of these integrated feedback effects that I'm particularly invested in is the question of cosmic enrichment. It is when and how was the universe enriched with heavy metals? We know from measurements in the local universe that the typical metallicity profile of clusters flattens at large radius and is still significantly enriched at a value of about a third solar metallicity, stretching towards the virial radius of these clusters. We've since extended those measurements to high redshift, including work I've done with XMM to constrain large-scale cluster metallicity out to redshift 1.7. And even at those redshifts, the gas is still significantly enriched. How is this the case? Why do we see so much iron enriching the bulk ICM that isn't localized around host galaxies when stars formed? We think the answer to that is clearly feedback. AGN feedback early in the lifetimes of these clusters that redistributed metals from host galaxies as the clusters were forming. And this is what's known as the early enrichment scenario. And this is a key example of how we can use these X-ray observations of the ICM to probe the history of feedback processes, but it also highlights how we need to think very carefully about making these measurements. The local universe measurements that I'm showing here were made with Suzaku. The objects were so bright and so large that you needed a mosaic to obtain profiles, and your signal to noise was very, very high. But at high redshift, it's a very different story. So when we think about how to push this work to higher redshifts, I want us to consider what I put here as the 3 pillars of instrumentation. So designing and using our flagship X-ray facilities is always a question of balancing spatial resolution in the form of your point spread function, your sensitivity, in this context, mostly in the effective area that you have at soft energies, and your spectral resolution. And while all 3 of these are very important for X-ray astronomers, today I will not be talking about spectral resolution. Clusters are extended objects, so gratings are not ideal, and currently there's a whole host of reasons why I'm not pointing CRISM at our high redshift cluster samples. But if you focus on the other 2 pillars, I want to say that it does depend quite a bit on what information you're trying to extract. For the cluster metallicity measurements I was just discussing, you really need independent measurements of metallicity at large radius. And that means you have to exclude the bright core where most of the cluster signal is. This is a very low signal to noise and even very low signal to background regime. So you need a lot of sensitivity to make progress at high redshift. But for other types of feedback studies, for example, identifying and characterizing cavities in the ICM or constraining the associated jet power, you need very high spatial resolution. So here I'm showing Chandra images from Julie Flavichuk-Larondo's work that use deep Chandra observations to extend these types of feedback studies out to redshifts of 1.2. And that's to say absolutely nothing about the natural point that there are cases where you absolutely need both of these pillars to make progress, like in order to produce these finely resolved temperature and metallicity profiles within clusters that I'm showing here out to redshift of 1. So this brings me to the main question that I put together for this talk. How do we best leverage our existing X-ray facilities, those being Chandra and XMM Newton, to probe feedback within clusters at high redshift? The answer to that really lies in the properties of clusters themselves at high Z. Like I said, clusters are spatially extended objects on the sky, but they still aren't large in this regime. At redshifts above 1, the characteristic scale R500 is only about an arc minute or less. And so that means if you want to resolve small-scale gas physics on the order of tens of kiloparsecs, say near cluster cores, instead of hundreds of kiloparsecs, you really need to use Chandra and its better spatial resolution. But not only does Chandra have poorer sensitivity than XMM, it's decreasing year to year due to contamination on board the telescope. And so for the work that I'm talking about today, it's at least an 8 to 10 times deficit in the cluster signal compared to XMM. And that's only going to get worse as we get longer into the mission lifetime and push to higher and higher redshift systems. And even if you want to use the larger effective area of XMM to make measurements, especially at large radius, you really need to be careful about contaminating point sources that are spread out by the larger XMM PSF. So altogether, there is no single existing X-ray telescope that can provide a full spatial description of the intercluster medium, but I'm sure many people can see where I'm going with this because joint observations reveal the complementarity of our current X-ray flagship missions. As an example to what I'm talking about here, I'm showing SPT 2334, a redshift 1.2 galaxy cluster observed with Chandra for over 100 kiloseconds and XMM for roughly a third of that time. I think you can see the center of the cluster on this screen, hopefully on Zoom as well, but you definitely can't see beyond that in the Chandra data. What you can see, though, is how well Chandra can localize that emission from the ICM, as well as that from point sources across the field of view. In contrast, the XMM image is much deeper, but you can also see the point sources here are much more spread out. Some are not even detected, and others are clearly contaminating the central ICM. These blue circles are actually from the Chandra detections that we've resized based on both the flux measurements from Chandra and our model for the XMM PSF. And basically this allows us to forward model AGN characteristics between Chandra and XMM to limit the contamination or residual flux from AGN down to a consistent level. So in principle, joint observations of high redshift clusters with both Chandra and XMM are extremely complementary, and they can help provide a fuller, more complete spatial description of these systems. And this is really how we've developed our approach to the targeted follow-up of clusters for studies of evolution. First, to know what clusters to go after, we do need a large sample of galaxy clusters in the first place. For this, we turn to wide-field Sunyaev-Zeldovich effect surveys. SZ effect surveys are very good at picking out the most massive clusters at a particular redshift without being subject to optical projection effects or X-ray cool core or luminosity biases. From these samples, we've made a really concerted effort to get joint Chandra and XMM coverage for many high redshift systems. In this figure for SZ cluster detections from Planck, SPT, and ACT, filled points here represent any X-ray coverage, not just joint, but there's a few systems that I want to point out that do have joint observations. They include XLSSC 122 at a redshift of 2. This was initially X-ray detected, but is a bona fide SZ detection as well. And it's essentially the highest redshift cluster we know of that now has this joint deep X-ray data. We also have SPT 0459, one of the highest redshift, most massive SPT clusters that currently provides the highest redshift measurement of metallicity outside of cluster cores. It's one of 10 clusters in what I'm calling the high Z metallicity sample, which provided those constraints on large-scale ICM enrichment that I was showing earlier. And we also have good coverage for a few dozen systems in the SPT 100 square degree survey in an effort to make sure we aren't only considering the highest mass systems in our studies. And further expanding this kind of joint X-ray coverage was where a lot of my proposal work was focused during my PhD. So we now also have joint coverage for some of the highest mass, highest redshift systems from ACT DR5. And In order to better connect the local and high redshift universe measurements, we also went and targeted some of the most massive systems below redshift of 1, where some had really nice XMM data, but the coverage for others was spotty and none of them had Chandra observations. So for high redshift systems, some of these observations can still be fairly shallow. We aren't going particularly deep on every single system. But to really hammer home why some of these joint observations are so important, I want to show an explicit example using this cluster, ACT 0123, which is one of the highest mass, highest redshift clusters from ACT DR5. It also just so happens to be the highest redshift dynamically relaxed system we've identified to date. And these types of systems, dynamically relaxed clusters, are very interesting to us. Galaxy clusters grow hierarchically. Major merger events can significantly disrupt the distribution and properties of the ICM and produce really interesting dynamics and irregular morphologies. But if you leave clusters undisturbed for long enough time, they will relax. They will trend towards high symmetry and hydrostatic equilibrium. The ICM within these systems typically presents with very sharply peaked surface and symmetric surface brightness and density distributions, and a corresponding central temperature gradient towards cooler temperatures. This is where we get the term cool cores. And we want to characterize cool cores because they are great laboratories for feedback processes. You have lots of rapidly cooling gas, but oftentimes not significant star formation because feedback from the central supermassive black holes provides enough heat to offset further runaway cooling that would otherwise be necessary to form stars. And so I can show here how ACT 0123 factors into that picture and also point out why it's a textbook example of why we need this type of joint data at high redshift. On the left, we have the Chandra image of this object, which shows the fairly symmetric, centrally concentrated X-ray surface brightness. It also detects point sources, and I'll specifically highlight this one to the northwest. In the middle, we have the XMM image, which is deeper, goes to larger radius, but it's also clearly contaminated by this bright source. So much so that it's difficult to tell the morphology of the cluster just from XMM alone. Without the high spatial resolution from Chandra, you might not know whether this was a blended source, a pre or post merging system, or just some really weird morphology. You really need Chandra to sort out the AGN contamination, and again, this really highlights the value of having this joint data. And we don't yet have any targeted observations at other wavelengths, but on the right here is a stacked GRZ image from the legacy survey. There's a really massive BCG right on top of the X-ray center of the ICM. So collectively, this is what led us to believe that it might be relaxed in the first place, and we can do a full imaging morphological analysis of the system, mostly enabled by Chandra because XMM can't resolve the inner regions of the cluster core because of its PSF. In contrast, though, only XMM can actually constrain ICM properties out to R500. Chandra just isn't sensitive enough unless we got megaseconds of observation. But the measurements we can make between instruments are consistent. Here you can see that we convolve the Chandra surface brightness profile, which is shown in red, with our model for the XMM PSF. That's plotted over top the XMM profile in blue, and things agree both within the cluster core and out to large radius. And so we can use all of this to actually quantify the relaxation of this cluster based on the two-dimensional surface brightness distribution. And those metrics line up very well with our previous cuts for dynamically relaxed clusters at lower redshift. The only spectra we have for this object, and really the only spectra we have for a lot of these high redshift clusters in our evolutionary sample, comes directly from the X-ray data. And so we can use spectra extracted from XMM to confirm the redshift of these systems. Here for ACTA 123, we have a very clear detection of the iron K alpha complex, redshifted to 1.5 to confirm its spec Z. But together, all of these observations identify ACTA 123 as the highest redshift dynamically relaxed cluster we've discovered so far. And if you combine spectroscopy from Chandra and XMM, you confirm the cool core, which is about 2 keV in the central 40 kiloparsecs, and it tells you more about the feedback history for this object. Here in the middle and right, I'm showing the density profiles of ACTA 123 combined from Chandra and XMM. And in the middle, I've scaled the density profile according to the self-similar expectation. So that's encoding the evolution in the conditions of the universe through the evolution function E of Z. And I've also scaled the radius in units of R2500. And you can see that when you're comparing that profile to the typical density profile of relaxed clusters at lower redshift, that's the band in gray, the centermost density is actually a little bit low. But on the right, we're zooming into the inner regions of that profile. We're making the same comparison of density, but everything here is in physical units. We aren't scaling for any evolution factors. The agreement here is actually better, and that's consistent with previous findings for relaxed clusters at lower redshift. Basically, the same feedback effects that stem and limit star formation can also keep the general state of the cluster core in a stable static state over billions of years. So the cores of relaxed clusters do not evolve self-similarly, they're effectively constant. And I think that's pretty remarkable that we see this good agreement when you combine results from clusters stretching from redshift 0 up to 1.5, which represents more than 9 billion years of cosmic history. And so now what we're doing is actively analyzing all of this new joint data that we have and combining it with previous measurements out to redshift of 2 so that we can do similar types of analysis and probe the evolution of clusters out to earlier epochs of their formation history, even if all of the cluster and data we have aren't as pristine and relaxed as the example I've just been showing. Okay, so to summarize the takeaways from joint studies using the current generations of instruments that we have, the X-ray observations that we can make of the ICM provide a really unique window into the histories of some of the most massive objects in the universe. We have a very high level of complementarity between our existing flagship missions, Chandra and XMM, that allow us to use these joint observations as an effective probe of the ICM at both small and large scales simultaneously. The recent efforts we've made to secure these joint Chandra and XMM observations for many systems at redshifts greater than 0.7 allow us to use them in evolutionary studies, even if they have relatively shallow data, like I just showed for ACT 0123. And I do want to say that these observations demonstrate the need, the absolute necessity for both high spatial resolution and high sensitivity for studies of high redshift clusters. And so they definitely serve as pathfinder work for any future next generation instruments so that we can make sure we have the same type of complementarity in the next decades as we do right now with Chandra and XMM. And with that, I'll wrap up and I'm happy to take any questions.
Hey, great. Thank you so much, Anthony. Any questions for Anthony?
So if you're designing new television for your science studying cluster, what would be the minimum angle resolution or minimum effect area you'd like to have? You have some numbers, to push this science forward.
Yeah, I mean, effective area is mostly going to scale directly with exposure time, like overall. But so I did a lot of work with Axis, looking at both the limits on the angular resolution as well as particularly the soft band effective area, showing that we definitely, as we push to higher redshift and things get redshifted even more, we definitely need really high softband sensitivity down to say like 0.3 keV. Even better if we could go lower, but that was pretty much the minimum there. With Axis, we could push out, say, like the metallicity measurements and the resolving AGN and looking everything there, even across the field of view with 1.5 arcsecond resolution. As you get, though, towards more like 5 to 10 arcseconds resolution is where you get into a bit of trouble as you try and separate emission from the cores and the outskirts. Something I didn't talk about here explicitly was we always do initial fits to surface brightness and density with Chandra, and that allows us to basically convolve our measurements in a large mixing model that accounts for both geometry as well as the PSF so that we can essentially deproject our results and we're not just doing everything in projection so that we can really get into those faint cluster outskirts. And that's something that, even though we're trying to make measurements at large radius, still can depend on the spatial resolution. So definitely like order arcsecond resolution is important.
Maybe added to that question, have you thought about New Athena? So like the arcsecond is, but I mean, you haven't talked about spectroscopy here.
Yes,
but,
I have.
For your possible science with New Athena, are you gonna prioritize both if it's translatable and achievable?
Yes. Mhm.
Like with WFI and XIQ?
Yeah,
Yes.
absolutely.
Which one wins? Or is it a combination of both?
Ooh, I mean, I would say definitely combination of both. I'm really excited for the XIFU, especially for these enrichment studies, because everything that I presented here today and all the metallicity measurements that I talked about, that's just the iron line. That's this, or the iron complex, because we don't have the spectral resolution. And so I didn't talk about it today, but spectral resolution can be really interesting to address these questions of enrichment, and especially enrichment mechanisms when you compare that to, I also ignored all the galaxies within the cluster, but if you look at their stellar populations, and so you might be able to constrain the production mechanisms of these elements as a function of redshift. And so that itself is very interesting, but I also need to know where that emission is coming from. And so if we are able to have the complement of spatial resolution and spectral resolution, you can really get at those questions. So ideally, yes, I would like to use both, which I know is a really unsatisfying answer. But yeah, so I am really excited for New Athena to push this forward. We just have to make sure we are understanding of the limitations of its PSF and hopefully pushing for the types of complements that we have with Chandra right now.
Okay. Any final questions, Francie? On Zoom? So I just have one very technical question, which is probably very silly, but when you showed the projected surface brightness that you can infer from the data, are you making any assumptions, like probably like spherical symmetry when you draw these onion eye?
Mhm.
Do you need to make any other assumptions? Or that's like
No, that's a good question. Everything here is pretty much under the assumption of spherical symmetry. I mean, we are extending a lot of our fits to be elliptical symmetry, so we're at least getting a little bit better. But in terms of getting into the three-dimensional structure of the triaxiality of clusters, that isn't something that we're attempting right now with these basic surface brightness analyses.
Okay, so with that, let's thank Anthony again and both of our speakers. Great. So we'll be back next week. So thanks a lot. And there's a